Continuing our discussion of reaction mechanisms in Chapter 18. In this case, we're talking about primary amide. Has to be primary amide or this reaction doesn't work. And the pKa of a primary amide, or any amide where there's an H on the end, if we had to guess, we'd have to go back to what we learned in Chapter 16, where the carbon attached to the carbonyl had a pKa of 20 on those H's. And nitrogen, being more electronegative than carbon, makes more stable anion. So it's easier to take the H off. The difference is 3. So 17. This is a new pKa, so I'm going to write that down. Just a reminder, primary or secondary amide, pKa equals 17. I am drawing the H off of both of these and erasing the second H. Crossing off potassium. Putting the anion on the oxygen because it belongs there. And it looks like the only difference in these reactions is the type of base I'm using. They both have very similar strengths, almost identical. But one of them has an extra H attached to the O, which we'll be able to remove later in the second mechanism, but not in the first. So the first mechanism is an abbreviated version of the second. It's great. We'll do the first one, and they'll say, hey, where we left off on this one, we got about 6 more steps in the next one. So here we go. We're going to do them at the same time. So we're going to take that H, generate a lone pair on the nitrogen, take that H, generate a lone pair on the nitrogen. Hey, there's already a lone pair on the nitrogen. This is when we're allowed to combine steps. Hey, there's already a lone pair on the nitrogen. We better tell the teacher we're combining steps. And baby blue's it's gonna cross over and hit the very reactive electrophile chlorine. Attack the very reactive electrophile chlorine. So you've dumped a chlorine onto the nitrogen. So this R group doesn't change for forever. I'm only going to circle it over here. It's the same R group on the other side. R attached to carbonyl, attached to N, still has an H, now has a Cl. I believe that's the same intermediate in both. Oh, not going to let me be that. You're just going to be mean to me. Sorry, talking to my computer. Going to go monochromatic. Okay. Anybody want to guess the pKa of the H that's on the nitrogen now? You think it's exactly 17 still? You said higher? Oh, you said lower. That's good. Yeah, a little lower because of what effect? Sorry. Inductive effect makes the anion more stable, means the anion's easier to make. So let's hit it with an excess of the base. And this time, oh, here we go. OCH3, why not green, since we're here. OCH3 green. Don't forget that anion. And instead of dumping the lone pair on the nitrogen and then resonating, I'm just going to resonate. And you're saying, wait, isn't that combining steps? And I say, no. You can do resonance in any mechanism. It's the same step. So I'm resonating all the way to the more stable O minus. N minus is not as stable as O minus. We know that from many moons ago. Same mechanism both times. R, O minus, double bond N. N has a leaving group on it. Wow. Yeah, we're gonna definitely need to extend our big black line.
For the second one, should that be hydroxide?
Oh, you caught me. Thank you. Yes, the base was not OCH2. I was so convinced we were doing the same thing, right? Oh, yeah, knew that was going to happen today sometime. There we go. And generating the same species. It's very important. Nitrogen has a leaving group. It does. So when we resonate down, we have two options. We can just do the resonance to get back to an N minus, which we're not going to do. Or we can break this bond and rearrange it. It moved over to the next atom. This is one of our many rearrangements. And Cl minus is a leaving group. It leaves. This is very cool, you have to admit. I gotta tell you how cool I think it is. It's a rearrangement. Those are always cool in my books. Rearrangement. You have just generated something called isocyanate. An isocyanate. Why is it called that? I don't see a charge on it. It's an alkyl isocyanate, named after its parent anion. It's an aside. Whoa, I don't even know how that happened. That's its parent anion, isocyanate. The worst chemical disaster in human history involved an isocyanate leaking into the atmosphere. It was Bhopal, India, I think 1980. Many people died. They're toxic. And you know, the population density in some places of India is very high. So they had the chemical company right next in a city. It was one of the saddest times in chemistry. But anyway, that's an aside. What are we going to do with our isocyanate? It clearly, this is the R attached to an N. So that N is going to pick up an H, isn't it? Because it doesn't have it yet. I'm just looking at where I have to go, people. This is an intermediate on the way to this at the end here, except it won't be an OCH3 here, it'll be an OH when we're finished. And that one will do many more steps to get to here. So we have our isocyanate, and now it's all about hydroxide and water. Every step will involve either or hydroxide and water until the end. As an acid-base conjugate pair, okay? And a nucleophile. Hydroxide's a good nucleophile. And when I said hydroxide up here, I meant methoxide, didn't I? Hydroxide's this one, as you so kindly pointed out earlier. And methoxide is the one over here. I got to try to remember which one I'm using. OCH3 minus here does the same thing that HO minus does here. First step, I hope you're not surprised, it attacks the incredibly positive carbon. Talk to me about why it's an incredibly positive carbon. 4 bonds to more electronegative atoms makes anything incredibly positive. Okay, that's step 1. I hope I have my red-blue comment at the top. Yep. Because O minus is going to resonate back. And here's where the reactions will be a little different. Or maybe not. Let's make them the same. I'm going to try my best to make them identical as long as possible. I think in both mechanisms, you need an H on the end. Where's the H coming from? I got an arrow to nowhere. Never a good thing. What did I say about from now on, you're going to be using OHCH3 minus and its conjugate base. There's where the electrons are going to go. Or you're going to be using OH minus and its, I know it's hidden, but and its conjugate base. No, sorry, conjugate acid. I've spoke backwards both times, didn't I? I apologize. I will say it again. OCH3 minus is the base. You will be using it and its conjugate acid right there. OH minus is the conjugate base. You will be using it and its conjugate acid water. So I repeat, conjugate acid is needed for a proton right now. It's been there all day. Don't ask where it came from. Sorry, things are a little tight down here. And don't forget the second arrow. Meow. What a strange teacher. Why am I saying meow? Do I have Tourette's? No, because I'm generating the conjugate base of this. Sorry, OH minus is the catalyst. I used it, I made it. Here, methoxide is the catalyst. I used it and I made it. If you're curious, you're going to generate CH3OH and HOH. Plus the more important final product here. You're done. I don't know how to show that without confusing you, but you also made the final product on this one. And we'll just come in with our light pink here and say, that is that. Are you not feeling it? I'm not myself. Here we go. This thing will become this thing because OCH3 attacks the carbonyl and pi breaks and remakes. So OCH3 attacks the carbonyl and it's back. The N picks up a proton and is now H. The R group never changed all day. You are done. This thing becomes this thing. And are you surprised it's called a carbam-8 ester? So named after this ion here called carbon-8. Why did I draw that there? Because I see it down there. So what does the AM mean in terms of how carbonate changed? Carbam instead of carbon. Carbonate has O there. Am implies what's there in the place of an O? What two functional groups begin with the two letters AM? Amide. Look, we have an amide, but it's also a carboxylic derivative down there. It's both. It's both an amide and a carboxylic ester in the same carbon. That's where that name comes from. We have a question? An arrow's missing. Which one? Right or left? On the right side? The O here? Oh, we didn't bring back for step 1 blue. Oh, thank you. I missed an arrow. I was supposed to reproduce my mechanism identically, right? I did not achieve that goal. Thank you for the correction. Saved us from having comments in our videos. And we're going to draw the carbamic acid here. What? Oh, I already got a spot for a plus. The carbamic acid looks like this. It's got a new H. It's got a carbonyl. It's got OH in green. And if it was OR, it was a carbamate ester. It's OH, it's a carbamic acid. Those are all unstable. Unstable. That looks like unstable. Unstable. A-B-L-E. And they will break down and generate a carbonate ion, as you see above. I'm wondering if I can loop this mechanism around that. You probably don't have that luxury. And just a point, for clarification, you made 2 things, water and that. And where do we have to get to? We have the pieces here. This is just R attached to NH2, R and H. So clearly, sometime you're going to get a new H on the nitrogen. This whole piece is going to be gone. How many oxygens are attached to carbon here? 2. How many oxygens are attached to carbon up here? If you want a picture, it's right here. There's 3. Want a better picture? Here we go. There you go. Better picture. Yeah, so where do you think the new O comes from? I need an O on the carbonyl. The new O. Where's it come from? What's the most nucleophilic O we got? OH minus number 5 is my guess. I might be off on that. But if you're OH minus and you have a choice of being a nucleophile and attacking a carbonyl, or being a base and attacking something with a pKa of at least as low as 5, don't you think this has to have a pKa of at least like 5-ish? Doesn't it look like a carboxylic acid? What do you think your choice is? 16 goes towards 5, or sorry, 5 goes towards 16. I said it backwards. Or attacking a carbonyl. Guys, acid-base reactions where the pKa is favorable will always happen first. Write it down, do something with it. If the pKa's work, do it, okay? You might have to undo it and then just say, oh, it was equilibrium was happening, but it just didn't get us where we want to go. And that's when chemistry, becomes interesting. First step, take the H off. Second step, you need another hydroxide. You will be using a ton of hydroxide. We've already used a ton. Second step, attack the carbonyl. Generate a lone pair. And I could do a third step, but I think your mind might not like it. So let's just do one at a time. Well, 2 at a time. We got an O minus. We got another O minus. We got, what else we got on? We got an OH, it's purple. And we're about to finish this thing off. should be able to tell me some of the things that need to happen. Is there a purple H in carbonate? Is there any H in carbonate? No. What's going to take the H? This answer is taking too long. OH negative. What do you think is going to happen to the pair of electrons in that sigma bond? Please look at carbonate. It's at the top of the screen. Make pi. What do you think is going to happen to the sigma bond between the carbon and nitrogen? Break and become what? Sigma bond between who and where? What? Why? N needs to be bonded to what? Another H, which is going to get from what? I told you for the rest of this mechanism, you're going to be using the combination of hydroxide and its conjugate base, acid. I misspoke again. Hydroxide is the base. Its conjugate acid is water. Thank you. We're going to use water. And it's all one. Although you could argue, and I like your argument, that you should protonate your leaving group first. Ah, no, Ali wants me to just do it. He wants it to look like a tautomerization. There you go. I will forgive you for not making a tautomerization into two steps. You can always get away with a tautomerization in one step. That's for Ali. There you go. And I think that gives you carbonate, right? You have your two O minuses. You got your carbonyl. Your nitrogen now has an H. And only one comment, rather long video, I told you. The stereo center. Why would I bother putting a stereo center? I just want to remind you, if there's a backside attack on a stereo center, it flipped. If the stereo center didn't do anything except in this step, it took its electrons and moved next door. It didn't get hit by anything, right? The R just slid over with its electrons. The stereo center didn't change. So look on old exams. This mechanism always has two products written, and it asks you to choose the correct product. The enantiomer will also be drawn. Don't pick the enantiomer as the major product. This one, the stereo center, is never involved in the mechanism. So don't change it. Pick the same stereo center. Just in this. All right. Big, big, big. Not that. Got the whole picture there, pretty close. And that's that one. One more activity today.